Yeah. Studying, I guess. Yeah, I liked. I think it's been continuing Sunday. Yeah, that was good. I felt a lot better. Yeah.
All right.
Yeah.
So I've got all right, so homework was posted. I hope hopefully it shouldn't be too bad. Good practice. Good practice to get practice for the exam. So the exam is going to be something like that as well, where you'll have the R document, the RMD document that has the questions and then the answer. And I did put in one of those questions where you answer a question, so you can see like where to put the actual type out your answer. So that's what I would be looking for. So we'll have something like that. So exam on Monday, it'll go live. Monday, we'll see. I think what we'll do is we'll reserve the lab, like not have technically lab or class at that time. I'll reserve that time where if you wanted to finish up or try to knit the documents, to get it uploaded, we can do it at that time. So if you get errors, I'm here to help you. I'm here to help get it uploaded. So those things will go live on Monday, and then you could start on it. You can go in different order. So nothing says you have to take like the technically closed book quiz. It's on Blackboard first before you do the RMD document. So if you want to do the RMD document first, you can. All right. So we'll use, for that lab, I won't go over new material. It'll just be, I'm coming in here to hang out and help you solve any knitting issues. All right. I will also help you solve any errors that you're getting. So as part of the exam stuff, I do think that if there are errors that I think you should have known and should have been able to solve, I can help you get them fixed at a point deduction, basically it costs you a point. All right. But if there's other things that I look at it and say, yeah, that's really not your problem, I'll help you get it fixed so you can continue. Because the last thing that I want to have happen is that you stumble on importing a data set, and then because you stumble on importing the data set, you can't answer the other questions tied to it. So that's kind of the way that the class, that the application stuff will work. It'll step you through the problems, doing the different steps. If you stumble at one step, then it'll be hard to complete it. So is it timed? The RMD document is not timed. It just has to be uploaded by the end of the day. But the quiz or the exam part of it will be timed. So yeah, review definitions, review the notes. I won't ask you to calculate means or medians or variances on that exam. We didn't do it by hand. We didn't have practice by doing it by hand. We did everything in R. So it'll be a mixture of maybe a fill in the blank, where you give me the terms. I might ask what's the variable type, and then you type in, or it'll be kind of like what we did with the quiz, where it's multiple choice or multiple answer type questions. Right. So fill in the blanks would be like rounding and implied limits. And when we have those, just know that I'll go back and check the answers. So whatever it tells you the grade is, that might not be your final answer. It's just the grade that was auto-generated from the auto-grader. Kind of like the Edgenuity auto-graders. I don't know if you said that the art stuff, that it looks for certain letters. So if my daughter got 100% on one answer, it said write 3 to 4 sentences. We wrote 1, and it was like an 8-word sentence, and we got full credit for it. So what it does is it looks for key words. So yeah, the news article, the guy just basically demonstrated. I write a couple sentences, and then I just start typing any word that I remember from that topic. And as long as you hit a couple, they'll give you full credit. Don't tell me that Edgenuity is actually teaching our kids like the material. They're learning how to get around a computer automated grader. That's what they're doing. I mean, just wait. I mean, can you imagine driving tests in 20 years that does that? It's like, they put up the big stop sign and say, what is the meaning of this sign? And then somebody starts typing in red, octagon, white, roadway. All right, so do you guys have any questions on the homework or calculating in any of the means and variances? I think if we had it by hand, probably would have had questions, but with the R, I think it's pretty easy.
I haven't been able to download the homework.
You haven't been able to download the homework?
Yeah, well, something downloads, but it's a blank.
Okay.
So, the homework is something blank. You gotta be kidding. It's never worked before. That's the first time it's worked.
So yeah, you download it. Just it should automatically. The computer should automatically associate the RMD files with RStudio. So it should automatically open it.
I swear it really was a problem.
All right. Anything else? Any other questions? Come on, let me take this attendance required to. Elvin. All right. So, if we don't have any questions, we will start on some new material. This will not be on the exam. So, I know I told some of you exam 1 will probably be the highest grade, the highest class average. It's probably 88 to 92%. Probably going to be a little bit higher this year because, especially with the R, it's a lot of simple stuff. We've been creating vectors. That's easy. All right. Once you've learned how to do it, we're doing it repeatedly. It should be simple. Reading in a data set. I mean, there's points for actually reading in a data set correctly on this exam. So it's like 3 points if you can get your data set in there. Our second exam, and that exam happens in, I think, 3 weeks after our first exam. So we don't have as long a period. That exam covers probability. Right, so probability is much more calculation. Bring your calculator. We'll use it on those quizzes. On that exam, I will be asking you to calculate some probabilities on the calculator. So you'll need a piece of scratch paper. All right. So probability. Why do we do that? Well, probability is the foundation of all of our statistics. That forms the field of statistics. Normally, what we do is we do our experiments, and when we do our experiments, we make assumptions, and then we compare what we expected from the data based on these assumptions to what we actually did observe. And what we're starting to do now is recognize that what we see is a product of chance events, or at least the end result can be a product of chance events. All right. That is our error. That's our deviation. That's our variation between experiment and experiment. So, we have to understand the probability. What probabilities affect these outcomes so that we can then start to look at and calculate p-values. And p-value is itself a probability. All right. So p-value is defined as the probability of obtaining data or value as extreme or more extreme than our observed value or data if that null hypothesis is true. You should just go ahead and memorize this. This will be asked. All right. So p-value, it's a probability of obtaining a value or data as extreme or more extreme than what we observe just by chance alone. And our assumption is that our null hypothesis is true. Now, what's going to be our null hypothesis? In basically all cases, our null hypothesis is that there's no difference, or that all of our data come from a single population. So basically, it's chance. The chance, our p-values, the probability of observing our data just by chance alone. All right? For really low values, then something other than chance is producing that result. What is that something else? Well, it could be our treatment that we initiated. All right, it could be the grouping variable that we have. All right, it could be a time variable. Who knows? Our assumption is that none of this affects our data, and thus everything affects by chance. All right, so know our p-value, probability of obtaining data as extreme or more extreme than our observed value if that null hypothesis is true. All right, so p-value is a probability. What is a probability? Well, probability is a likelihood that an event can happen. You're probably familiar with it. If we have a 6-sided dice, what's the chance of rolling a 6? 1 out of 6. Right? You've probably encountered that. What's the chance of winning, the pick 3, the daily 3 lottery? Anybody? Daily 3 isn't too far. Too bad. You've got basically 1,000 different numbers, 0, 0, up 0, 0, 0, all the way up to 9999, right? So it's 1 out of 1,000. Right? So we have these probabilities. When we talk about probability, well, how we abbreviate it is P of our event. Right? So P and then the event in parentheses. That means the probability of an event. Now, our probability, the likelihood that an event can happen, is equal to the frequency of that item in our population. Right, so, example here is a jar of marbles. We have 200 marbles in that jar. That jar has 4 different colors of marbles. We have red marbles, blue marbles, white marbles, and green marbles. Our red marbles, we have 120, blue marbles 40, white is 36, and green is 4 marbles. All right, so the probability of any one of those marbles, of reaching in and grabbing a single marble, the probability of getting a specific color is equal to its frequency. So for our red, it is 120 over the 200 marbles that we have there, which is 60%. So we have a 60% chance of reaching into that jar of marbles and pulling out a red marble. Blue marbles, it's 20%. That's 40 over 200. Right? The white is 18%, so it's 36 out of 200, and the green is 4 out of 200. So another way to kind of write it down is that our probability of the event is the number of ways in which it could occur, so the number of combos over total number of combos that are out there. All right, so in this case, the number of combos that we have, well, we have 120 red marbles. All right, the total number of combos that we have, 200 marbles. All right, so that's our frequency. It's also probability. So our expected value then is the weighted average of all possible outcomes. We define this as the number of replicates that we're going to run times the probability that an event occurs. So, example here, I said, let's say we have 400 marbles. All right? How many green marbles do we expect will be in that sample if the chance of putting them into that jar is equal to these probabilities? Well, the probability of being green, having a green marble, taking it out and putting it into our new 400 jar marble, or 400 marble jar, is equal to 0.02. And how many marbles do we have in there? We've got 400 marbles to begin with. So 400 times 0.02 gives us an expected number of 8. Simple, kind of. You can think of expected value as like an average. All right? An average. So if we roll 2 dice, we go to the craps table. Hopefully you're all familiar with craps. Seen it's played on TV. Rolling the dice, right? 2 dice out there, right? what is the most common outcome when you roll those two dice? 7. How did you get that? What's that?
What are the numbers on the dice out of 7? 1 and 2.
Yeah. So when you add up the numbers, yeah, the most common number is 7. So 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. Right? Yeah. How many different combinations? 6.
Oh, just for 7.
Yep. Six combinations out of 36 total. All right. So, all right. If we think about, if we rolled those two dice, and we said we rolled it, let's say 100 times. We went and played craps and we rolled the dice 100 times. How many times do we expect to roll a 7? Well, it would be 100 times 1/6 because it's 1/6 chance of rolling a 7, and that gives us an expected number of outcomes. If we flip a coin 10 times, how many heads would we expect? Well, we'd expect to get 5 heads. It's 50% chance of flipping a head. We flip the coin 10 times, we'd expect 5 heads. So that's our expected value, and we can use our expected value to generate our expected observed values if we have discrete variables. All right, and we will do that. We will do that, and that's why we introduce it here. All right, so probability introduces this element of chance. And we have chance events that happen when we perform our experiments or collect data. All right, so stochasticity is that element of chance. All right, so stochasticity just means randomness, random events. The opposite of stochasticity is deterministic. All right, so if we can write an equation, mx plus b. What is that equation? It is the equation of a line. All right, so that line is a deterministic equation. Right? If we are working with the data set or an experiment that is entirely deterministic, if we know our x, we know our y all the time. Right? That's deterministic, but let's add an element of chance to it. Now, we know x, we should be at y, but the stochasticity is going to give us actual values. Some of them may be on the line, but a lot of them are probably going to be off of the line. That range, deviation from what's expected, that is our stochasticity. All right, so here's our marble example to kind of demonstrate this. All right, we're going to use R. All right, so you can open up RStudio, get it going, and that's what I'll do. And what we're going to do is generate some random numbers. Shrink this down for you all. All right, so what we're going to do is do marble examples, and we're going to do them, kind of one by one, so we can talk about what we're getting to just demonstrate stochastic events. We're going to use the R multinom function. So your guess, we're going to use multinomial distribution, and then this R in front of it means that we're going to select a random number from that distribution. Well, what's a multinomial distribution? Well, let's take a step back and says, what's a nominal variable? It's a categorical variable, right? All right. Binomial means we have 2 outcomes. Presence, absence, true, false, male, female, yes, no, that type of thing. Multinomial distribution means that we have more than those 2 outcomes. And for us, we're going to use marbles. So for us, we're going to have 4 different outcomes. We can have red, blue, white, and green. All right. So what we're going to do is generate a distribution from the multinomial. So randomly generate. Where's my cursor? There it is. Randomly generate a distribution or a data set from the multinomial distribution. We have a number of samples, we have our size, and then the probability. What do all these mean? Well, the probability is a vector of probabilities. We're going to use our probabilities from the previous slide. So you can see we have 60% for the red, 20% for the blue, 18% for the white, 2% for the green. All right, that's our probabilities. That's our frequencies in which we're going to draw our actual samples. We're going to draw one sample. Each of us will draw one sample. All right, but our sample is going to consist of, to start off, 100 marbles. All right, so out of these 100 marbles, this random number generator is going to tell us how many red, how many blue, how many white, how many green marbles we have. All right, so go ahead, using this equation. This does it for n equals 100. All right, so go ahead and run that. I'm going to open up my RStudio, and then we're going to see what we all get. And we're not going to set the seed. I mean, that's we don't want to get the same numbers here. So I'm going to make a new markdown document. Note the vector, so probability needs a vector of probabilities. We will have to do something similar when we do a goodness fit test, and we're comparing observed to expected counts. Right? We can give it expected counts, so most likely one, the example that we'll use is Hardy-Weinberg crosses, so 9 to 3 to 3 to 1 ratios and so forth. All right, so did you run it? Here's mine. All right, and on this one, I get this count. Now it's not labeled, all right, but we know how we arrange the probabilities. It's red, blue, white, and green. So this is what I get. All right, I only have 53 whites. I'm sorry, 53 reds. I expected 60 reds. Now and that's different. I'm not saying I should have obtained 60 reds, because nothing says I should have actually received it. That's not a deterministic equation. We have an element of chance affecting our selection. So for me, I had 53 red marbles. All right. How many marbles did you get? How many red marbles? How many? 58. Bethany, how many did you get? 67. Jeez, oh man, yours was a lucky red marble. All right. So and I'm sure all of you are going to be different. All right, all of you are going to be different. Now let's switch it up. I should say, let me move this over. When I did this, I think the green. I don't know what I did. I thought I put them up there. Let's do 500. Right, and see what we get. So I'm just going to change this 100 to 500. So now we're still going to just do one sample, but now we're going to draw 500 marbles. Okay, so 500 marbles. If I use my expected calculation, my expected equation, it's 500 marbles times 60%. So my expected is 300 red marbles. I had 318. Expected 300, I had 18 more. Okay? Did anyone get exactly 300? Did anyone get like 301 or like 2099, like 299? No, our expected, on average, we should have had, we should get 300, but random chance is going to give us a value. If we repeat this over and over again, yeah, we're going to probably get close to that. And let's do one more. Let's do 1,000. So now out of 1,000, we should see 600. Now I'm close. I'm right at 601. What did you get?
598.
598. What did you get?
599.
599. 599. 601? 609. Okay, so yours is a little off. So, all right, as we increased our sample size, what's happening is that we're going to start converging on our numbers on the actual average, on the expected frequencies. And that's what I have here on this slide. All right. In this case, instead of looking at red, I did green. And what I did was I repeated this over and over and over again. So here, it was just whoever's here in the class and whoever's following along at home. Right here, Will Jones says, yes, he had 300 exactly. Cool, that's awesome. That's on that end 500. He hit it, but you know, all of us, you were kind of around it. As we start getting more and more samples, we're going to start zoning in onto that average itself. All right, so when I did this, and I think I did it out of like 1,000 trials. So think of 1,000 students in the class. With the green, I counted up the green. How many I had? All right, I didn't just count up the green. I actually calculated the probability of green. I had a range from 0 to 8% of those marbles in that 100 set were green. So I had samples where I had 8 green marbles. I had samples that had 0 marbles in it. All right? And that range, 0 to 0.08, produced a standard deviation of 0.0145. So we had kind of a wide standard deviation. As I increased 500, all right, I had a minimum of 4 marbles, or close to it. Actually a minimum of 2 marbles, I believe. 2 marbles, but I went up to 0.042. All right, so our range started to narrow. And then it narrowed even more when we got to 1,000. And look at that, 0.05 to 0.035. We still had variation. We still had the bottom, but we were narrowing it in. Now, our true, probability of getting that green, what was it? 2%. That's what our expected is. And you can see our range, we should have had 0.02, really wide. And then we started to narrow it, and now we're kind of narrowing it even more. All right? And that's what's going to happen. The more samples we have, the more we start to converge. The more our data starts to converge onto the expected values. All right, so as our sample size increases, the probability of our event, so our frequency, starts to approach its true value. All right, so our averages start to really hone in on it, on that true value, and our dispersion also decreases. All right, questions? All right, so random. So that is kind of an idea. I believe it's the law of large numbers. So as you start to increase your sample size, we start converging on the true values. All right, so why do we talk about this? Why do we talk about these marble examples? Is because anytime we're doing data analysis or data collection, we are striving for random samples. All right, we strive for random samples. If we have a truly random sample, then we have an unbiased sample. All right. What does it mean by unbiased? It means that our sampling frequencies in our data set, that data set that we collected, are the same frequencies that exist in our population. So what we sample is the same as what's in the population. Going back to our marble example. This is 1,000. This is our population. All right, 0.6, 0.2, 0.18, 0.002. A truly unbiased sample will generate frequencies in this distribution that match these frequencies. All right, that's our goal. We allow error because that's our precision. The precision measure is what affects how close we are. Bias is systematic deviation. All right, so how do we do that? Well, if we know our entire population, then the way we go about approaching this unbiased sample is to assign a number to every single individual in that population. And then we randomly draw numbers, and those numbers, the individuals with those numbers, that's who we experiment on, that's who we collect data from. All right, so we've basically randomized who we measured. Most of the time we don't know that. Most of the time we can't, or we don't know the entire population. So how do we handle that? If we don't know the entire population, then what we have to do is we're going to try to take a subset of it and measure or take data on that subset. How we approach a subset kind of depends on what we are actually trying to measure, all right? Who we're measuring. All right, so one possibility is to randomly select our data points via a computer and then go out and select grids or establish grids. So in this case, if we wanted to go out and look at tree diversity, and what we would do is we'd go out to a forest and we'd have a computer pick random points across that forest. And once we get to that forest, then we drop our grid and we collect only in that grid. All right? We didn't just go out there and go along the trail and say, well, the trail is easy to walk through, so we're going to set up our grids along the trail. We've just biased our sample by doing that. The computer ignores that and actually gives us clearly defined spots to collect, and it'll be randomly generated points. Another way, if we went out to that forest, is we pick a starting point. We go out and just kind of pick a starting point, and then what we can do is take a spinner and spin it, and whichever way the arrow points, that's the direction that we're going to walk. How far do we walk? We're going to need another random number generator to tell us how many steps to take. And then once we get there, then we can drop our grid and start collecting there. If we were doing more of a transect, all right, perhaps we were going to measure every tree that we encounter, we would do the same thing. We'd get a direction, we'd figure out how many steps, and then as we proceed along that line, we could say anything within arm's reach gets measured. All right, everything out of arm's reach isn't. We're adding an element of chance that allows us to kind of generate a random trajectory across our landscape. If we're here at ASU and we want to survey the students, let's say we want to test them for COVID-19, and we need a random sample, how would we do it? I think this is probably why some of the big schools have such large numbers. How would we do a random sample of students? Say we wanted to sample 500 students. 500 students today, and then 500 students next week, 500 students the week after that. How do we collect a random sample? What's that?
I don't know. You have a sample from like every dorm, every classroom. On campus, off campus.
Okay, yeah. Okay, so if you get, I don't know if the people at home heard, so we have to sample, we have to make sure we get like the dorms, the different dorms, different buildings, different majors and so forth. So how do we do that?
Isn't there just a list of student names?
Yeah, okay, so list of student names or list of CID numbers. And then what we can do is just randomly generate, take out 500 names from that list, and those are the people that get randomly tested.
If you make sure that you get it from like the dorms and like every major, would that be random then?
No. So it wouldn't be. So if we said, well, we're going to go and we're just going to make sure that our sample includes people from the dorms, then what happens if our random sample out of 500 only has 100 people in the dorms? All right? The researcher, we should be indifferent as to how it was generated. We generated our random numbers. If we look at it and say, hold on, we actually have 50% of our students in dorms, but I'm only sampling 100 of them. If I go back and manipulate that number, we've now introduced bias. So we have to rely on the fact that we are getting a random sample. It might not be completely reflective, but we've generated our random sample, and then when we repeat it next week and the week after that, things should start balancing out. It's just the random nature of drawing the random samples. But I'm glad you didn't tell me, oh, we're just going to wait out of cabinets and every student that walks in is going to get tested. That's not a random sample. But that I suspect that's how some schools did it. They kind of went into the student quad and funneled people in there as the person's looking at their watch saying, I'm late to class. This teacher's going to kill me if I don't get there. They see the line and say, crap, I'm going to run. All right. He starts walking in the opposite direction, and then you probably would see administrators, hey, you, get back here. We got to test you. Then they take off running. You could just imagine a movie like that, right? They need it. Yep. Yeah, generator for CID, random number generator. Excellent. All right, so our goal with this random number is to get it so that these numbers, oops, I had it, I pulled my R, that this random number, this breakdown reflects the actual breakdown in the population. Now, if our sample is sufficiently large, then yeah, we're going to probably approximate it to what the population actually looks like. So we'll probably approximate, the sex ratio appropriately. We'll probably approximate the classification distribution, so freshman, sophomore, junior, senior type of classification. And that's a good thing. That's a good thing. We want that. All right, so how do we take a random sample in R? Well, let's try it out. So crickets.csv is posted. All right, so download it. We're going to load it into R. All right, I want you to call it dat.crickets because that's what I use for the code in this presentation. All right. So as you open it up, you'll see that we raised 100 crickets. With the crickets, we gave them an individual ID number. Right, so maybe used a tag that we super glued to their back so we could identify them. That's a cheaper option than the compared to the RFID chips. Okay. In this population, we discovered 5 different phenotypes. We are interested in susceptibility to infection, or let's say a bacterial infection or a yeast infection. Right? But we don't want to favor one genotype over the other, so we need to randomly draw 20 crickets across our population. So how do we actually do that? How are we going to do that? I'm going to show you how to do that in R. Let me open up mine. Dat.crickets. You can say streams. Don't forget strings as factors. Those of you. Actually, if you do import from base, you should have it. All right, did you get it in? All right, so here, we're going to generate our sample by using the sample function. With the sample function, we tell it the vector x that we are sampling from. So we give it the vector and we say, okay, we're going to draw our sample from this vector. All right? And then we tell it the size. How many samples do we want to draw from this sample? And then we have an option. After we draw a sample and we record the ID, should we put it back in the sample before we draw our second one? Or should we set it off to the side and draw another sample? So are we sampling with replacement or are we sampling without replacement? Right, so the lottery, Powerball, is sampling without replacement. Because you have all those, I think, 60 numbers in there, plus the Powerball. So once you draw a number, that is out of the pool. That's it. We drew that number, and then we draw the next number, and then we draw the next number. All right, you don't get repeats. But like the daily 3 and the daily 4 would be a sampling with replacement. Because you've got 10 ping pong balls in one container. We sampled it, we recorded the number, then that second machine that has a brand new set of 10 balls is the same as us putting that initial ball back and drawing one new one. So you can get repeat numbers. All right, and that's really the difference. If we sample with replacement, we can get repeat numbers. If we sample without replacement, we won't. All right, so for us, what we're going to do is sample without replacement. Why? It's because when we draw our crickets, we can't expose it multiple times to this virus or this bacteria or this yeast. All right, we're drawing individuals to see who's going to participate in our study. So we need 20 unique individuals, and that means we're going to sample without replacement. How do we do that? We use our sample function. So back in R, started doing this. All right, so we're drawing a random sample from a data set. All right, that's what we're doing. We're working with cricket.csv dataset, and we will use the sample function. Sample x size replace function, where x is the vector we are sampling from. Vector from which size is the number of samples to draw, or number of items to draw. We'll change from samples to items. And replace is t, so sampling with replacement, or f, sampling without replacement. All right? We're going to use both in this class. All right? Sampling with replacement is the basis of bootstrapping. Some of you that have done phylogenies and heard about bootstrap supports, that is a sample with replacement type of procedure. And I'll show you how we can generate bootstrap confidence intervals. All right, we'll also do sampling without replacement as a form of randomization tests. All right, so what we're going to do is we are going to sample, all right, our vector. So what is our vector? Well, we're sampling the ID. All right, so we have our data set, dat.crickets. Move that over. All right, and it's the ID variable that we're interested in. So we need the ID of which cricket we're going to use. So that is our vector. Now our vector is actually inside a data set. So remember, we will have to use the $sign in order to access that vector. And then our size is 20. And our replace is false. We were sampling without replacement. And then when I draw this, when I run it, it gives me the IDs of the crickets that I need to use in our experiment. All right. I could do one more thing. I can issue the sort function. My numbers are going to change now because I'm going to run it. But the sort function kind of puts things in order for me. But every time you run it, you're going to get a different number. So, so I'm just going to put down here, sort will sort a vector from small to large, or alphabetical if we're working with the string, with character vectors. All right. So we normally don't use sort for the rest of this class. When we do bootstrapping, we don't need the sort function. When we do randomization tests, we don't need the sort function. But we are going to use the sample function. So we've just generated a random sample of 20 crickets. All right. So real quick, just remember, X must be a vector. So use the data $sign variable format to access a vector or a data point that is in, or a vector that's in a data frame. And then when you are running these bootstrapping and the randomization procedures, I say don't set the seed. All right, we want it to be random. All right, that's what we want. All right? If we set the seed, then every time we run it, we get the exact same numbers again. All right, so what we're doing is we're going to let the computer time serve as our seed when we do this. Questions? All right, what we're gonna do is pick this up on Friday. We've learned random samples, all right, and then what we're gonna do is work with some probabilities. All right, we're good. Just remember, Monday I'll be in here for lab, but we're not gonna go over any of our classes.